So, shall I start?
Yes, please go ahead.
Yeah, thank you, thank you. So, good evening, everyone. So, myself, Rajesh, and I'll just talk about the cost-effective large area gaseous detectors for detection of charged particles. So, the detector that I'll be talking about, they are mainly RPCs or resistive plate chambers and MRPCs. And we have some very special features of these RPCs. So, during the course of my talk, definitely I'll be talking about it. And then I'll talk about the journey towards the development of the oil-free backlight RPCs. And of course, we had many failures over the journey, and how we developed a small, which is 30 centimeter by 30 centimeter oil-free backlight RPC, and ultimately, which led us to the development of a large oil-free backlight RPC. By large, I mean it is 2.4 meters across 1.2 meters. And I will summarize the results for the backlight, oil-free backlight RPCs. And I'll move on to multi-gap resistive plate chamber. We have an extra advantage of the time resolution measurement over the conventional resistive plate chambers. And I'll emphasize on the development of oil-free MRPCs, which is I'm sure that it is the one of its kind and is the first time development of oil-free MRPCs. And I will summarize a few results from those MRPCs. So as we will all know, this is a schematic of a resistive plate chamber where I have two very high resistive electrodes, the top one and the bottom one, and both of these electrodes are separated by a very thin gas gap. Typically, it is around 2 millimeters thin gas gap, where we purge in some known amount of gases in some fixed ratios, and which undergoes ionization process as any charged particle passes through the detector, and we apply very high electric field at the outer surface of this high resistive electrode, which essentially helps us to separate out the charge pairs that is formed by the ionization, as well as to enhance the charges. And then ultimately, by some mechanism or by some technique which we call as read out strips, we used to read those charges, and we used to locate the area or locate the position where these avalanches are formed inside the gas detectors, and we pinpoint the location or through where the charged particle has passed. The operation, to just quickly go through it, we have two modes of operation. One, we call it as avalanche mode of operation for an RPC. We also call it as a low gas gain mode, where the gas gain is typically in the order of 10 to the power 6. So this is a low charge. Here we have low average charge per signal, typically in the order of 1 picocoulomb. And since the charge content per signal is less, we need preamplifier and amplifier, which essentially increases very significantly the number of electronic channels we need to read these signals. And the gas mixture typically, but this is not a very golden rule or not a standard or fixed gas mixture, but typically which the gas mixture is used for avalanche mode operation is R134A is to isobutane is to SF6 in the ratio of 95 4.5 is to 0.5. The next is your streamer mode, which call it a high gas gain mode, which is where the gas gain is much larger than 10 to the power 6, where we have the average charge per signal is approximately, or it's more than actually, I should say, a couple of times hundreds of picocoulomb. And since the signals are very large, or the charge content per signal is very large, we do not need preamplifier or amplifier, which significantly reduces my number of channels. And of course, the cost also reduces very significantly. And the gas mixture, typically we have an extra gas, an added gas in this particular gas mixture, which is argon, then is to R134 is to isobutane, typically in the order of 55 is to 40 is to 5. Now, throughout the worldwide, whatever experiments, which all experiments they use resistive plate chamber, they're electrode materials. They're mainly of two kinds of electrode they use. One is the backlights, and the advantages or disadvantages of backlight, they're very less fragile than glass, and they can be operated in streamer mode, which is an advantage for the backlight RPCs, and they're very high prone to impurities, and because of this prone to impurities, we used to coat the inner surface of the backlight with some special kind of oil like linseed oil or silicone oil just to protect their surfaces and to operate them over a very long period of time. And for glass RPCs, they are very less prone to impurities, but they are very fragile. And with the glass, we have an extra advantage over backlight. Till now, that was a thinner electric plates can be manufactured. By thinner, I mean approximately in the order of 700 micrometers glass plates, which essentially can lead us to the fabrication of MRPCs, where we can have very better time resolution than an RPCs. And of course, since their surface is very smooth, we do not need any kind of oil coating. Now, we made our journey towards the development of oil-free backlight RPCs, and we wanted to look into the advantages, that why do we need to develop the oil-free backlight RPCs. The major advantage is that it can significantly decrease the cost of per chamber. So when we have oiling in the inner surface of the backlight RPCs, my price increases. But if we can produce the backlight RPCs without any kind of oil coating, then my price reduces significantly. But the major challenge is that to limit it or to operate it over a very long period of time, because its inner surface, if you not use any oil, the inner surface gets affected. You can see is the effect of not using oil, and it essentially do not allow you to operate your RPC over a very long period of time. So we tried a lot for approximately around 3 years, but finally we could succeed. But before I go to some of the successful results, we have some failed results. So a couple, I want to emphasize that one of the sample that we used, which call it as P301 sample, as you can see from the figures 1 and 2, what we did is we fabricated the RPC, and the basic characteristic, the IV characteristics, we tried to study of that RPC. And we can see that while ramping up, the blue dots, they shows the current versus potential versus current of the detector while ramping up the detector, and the red one while ramping down the detector, they do not follow the same pattern. And we had a look into this in quite a details. For that, we had to break the RPC, and when we broke the RPC, we could see under the microscope that some very small hill kind of structure we can see on the inner electrode of that RPC, or what we call it as the oil accumulation, the oil that have been used to coat the inner surfaces under the action of very high potential or high electric field inside the detector. They accumulated into small droplets, which essentially causes our detector to malfunction. And we approached one company in India for whether they can produce this oil-free backlight sheets. Some backlight sheets where you do not need oiling, and we had a lot of emails and communications. Even the company persons, they visited our laboratory, and after some 6 months to 1 years of hard work, they finally delivered us some backlight samples. And we developed, to start with, we developed a small 30 centimeter by 30 centimeter with a gas gap of 2 millimeter RPC. We operated it in streamer mode with a gas mixture of argon is to R134 is to isobutane in the ratio of 55:40 is to 5. And we could see a very nice IV characteristics for the detector, and we were initially were pretty happy. And then we could see the current stability performance of the detector for the initial 50 hours of operations, and we could see a very stable behavior in its current. And then we went to the characterization of the detector, where we detected the cosmic muon detection efficiency with the cosmic ray test setup in our laboratory, and we could see that our detector, it could achieve an efficiency of approximately 98% for the detection of muons. We also studied its noise rate of the detector, and we could found that the maximum noise rate we could found was 1.7 hertz per centimeter square at 900,000 volts. And when we had the successful results of a small prototype, we could think of developing a very large one. So we essentially ordered very large backlight sheets of the same material, of the same texture. We got 2.4 meter cross 1.2 meter backlight sheets, and we developed these RPCs. So here On the picture 10, you can see the size of the detector which I have put with respect to some the normal standard A4 sheet paper that we have. And while fabricating this detector, the major problem, one of the we face several problems, but one of the major problem that we wanted to highlight was the glue that we used during the fabrication of the detector. So we initially the standard glue which we used, it failed. It was successful for the small detector, but it failed for the large detector. Then we had to do some R&D on the glue structure also. And here I show you some results, especially the bulk property results of the glue for some 6 different samples, among them the sample 6, which is essentially a combination of BC600, which we use to fabricate our scintillators, plastic scintillators, and araldite. We mix them into some particular ratio, in the 1:1 ratio, and we use the hardener for the araldite, and we made the glue, and which actually worked to fabricate the large detector. And this large detector we also operated in the streamer mode, but with a different gas mixture than the smaller one, where the argon percentage was a little bit low. So argon is to R134 is to isobutane. This was 34 is to 57 is to 9. And the gas gap, that was 2 mm gas gap, and the gas flow rate which we kept, it was approximately 0.75 liters per hour. The figure on this one, figure 11, you see you see that it is the IV characteristics of the detector, and the inset figure, it shows the IV characteristics towards the low voltage applied on the detector, and we could have a gas breakdown voltage of at around 7,000 volts. And we measured the bulk resistivity of the chamber, which we got approximately in the order of 10 to the power 13 ohm centimeter. And finally, with this big detector, we could we were able to measure the noise rate as well as the efficiency of the detector. By efficiency, while measuring efficiency, we gave a signal threshold of minus 20 millivolts. So it's a very large signals. We have signals in the order of hundreds, 150, 200 millivolt signals. And the efficiency plateau, which got beyond 8,400 volts with an efficiency value of greater than 95%. So we are pretty happy with the performance of the detector. And the noise rate, we got it approximately 0.75 hertz per centimeter square. It was a little bit lesser than the smaller chamber. And then, since it's a very big detector, so we thought of making the efficiency measurements all over the detector, and we could select some 16 regions over the detector. Out of these 16 regions, 8 regions on the outskirts of the detector and 8 regions in the central part of the detectors. And we measured the efficiency of these regions, and we grouped them, and we could got the histogram, and we can see in the histogram in figure 15, you can see clearly that we have 2 very distinct groups. So the group which has higher value of efficiency, these are the locations which are located in the central region of the detector, we say. And the group with a low value of the efficiency, these are the peripheral region of the detector. So this is mainly due to which we call sometimes the edge effect of the detector, where there is a distortion of the electric field inside the detector at the edges, as well as a distortion in the gas flow rate of the detector at the edges. And then our main aim, then we shifted to the time resolution measurement of the detector, which we measured using 16-channel PS71860 DC module. And we measured the time resolution of the detector. We corrected it for the scintillator correction, and we measured as a function of the applied high voltage. And the best value, of course, with the scintillator correction, which we got was less than 1 nanosecond, which is 0.83 nanosecond at 9,000 volt. On the right side of the figure, I show you the best TDC spectra that which we got for our detector, and of course this was at the central part of the detector. And once this was successful, the development for the for a large detector, we thought of taking the long-term operation of the detector. So we kept the detector in a high voltage and gas gap, high voltage and gas flow for a period of 10 months, and then we monitored the detector for next 2 months. So overall, we kept it for 60 to for 12 months operational, but we monitored only for the last 2 months. And on the figure 18, you can, yeah, I'll just conclude it. In the figure on the figure 18, you can see the current performance of the detector, surface current, and you can on the figure on the 19, you can see the efficiency performance of the detector, which is very quite stable even after 1 year of operation. We measured the noise rate, which was found again stable, and also the time resolution which measured, it was also approximately very close to 0.83 nanoseconds. And so summarize this one, the large detector, we are successful to develop a detector of approximately 3 meter per meter square area detector, which was, we are very happy with this performance. The main advantage, we eliminated a very complicated industrial step to code, that is to code the inner surface of the detector, which ultimately gave us a significant reduction in the cost. We could operate it in streamer mode, so significant reduction in the electronic channels. So essentially, again, a reduction in the cost. And if I tell you very honestly, the total cost, fabrication cost of this detector, large detector, it was less than 100 USD. Then we approached the company to give us some thinner electrode plates, so that we can make some MRPCs. So MRPCs in between two outer plates, we put some inner electrodes. We divide the gas gap into n number of parts to enhance the time resolution. And here you can see we have the outer plates of the detector, and we got some 6 number of inner plates, which are approximately 500 micrometers thick, which are even thinner than the glass electrodes. So we are very happy with the 500 micrometer plates. And with that, we developed two couple of modules. The dimensions I have listed over here, the dimension of the modules. And we characterized these two detectors for this efficiency and noise rate, and we could successfully achieve close to 85% efficiency at an operational voltage of 16 kilovolt with a noise rate of 1.85 hertz per centimeter square with a signal threshold of minus 10 millivolts. And we measured the time resolution of the detector, and this was a 6-gap MRPC. And for the 6-gap MRPC, the best time resolution which we got was approximately 150 picosecond at 16 kilovolt of operation. And to summarize the results of this MRPC, yes, it was a very difficult goal to achieve for MRPC because manufacturing such thin backlight sheets was very difficult for the company. So thanks to the company once again, that we could achieve it. And we are towards the improvement. We are currently we are in the direction of improving the time resolution even further. And we also tested one point that I wanted to highlight is that we already have pointed out that these MRPCs, we can use them for some societal application, like for top pet imaging using MRPCs. They have that top pet machines. If we use MRPCs, we have several advantages over the conventional PET machine that we have worldwide. That we can have better results with much lesser per scan cost. And for that, we need to address a couple of issues first. So we are also trying to solve those issues. So along all these works, these are the references that we have, and thank you for your attention. Any questions, please?
Thank you, Rajesh, for you are still on time, so we have time for a couple questions. Okay, there is one participation online.
Professor Rajesh, I have a couple of questions.
Yes.
Compared to glass RPC and the backlight RPC, which is most efficient one in terms of efficiency and uniformity?
In terms of efficiency, backlight and backlight RPCs, they are also very highly efficient, as you can see from our results. We are close to 98% efficiency, and this sustained over a period of 1 year of operation. So I would say yes, backlight RPCs, they are also very much efficient, and One major disadvantages of the backlight RPCs was a thinner manufacturing of the MRPCs was not possible till date, but we could successfully manufacture 500 micron sheets. And if I remember correctly, for the glass MRPCs, they are approximately 600 or 700 micron thick. So yes, a backlight now, with backlight, since we can produce, or we do not, if we do not need any kind of oil coating, then yes, we have an extra advantage of backlight that we can operate it in streamer mode, whereas in glass you cannot, you literally cannot. So the number of electronic channels reduces backlight significantly. So yes. So
Before going
operations are
to multi RPCs,
We are already out of time. So we want to thank to Rajesh for his participation. Thank you very much.
thank you.